Welcome to the second lecture of week 3, which is on examples of laws of comminution. This lecture 2, where I am discussing different example, it will have two different parts. In part 1 I will consider 2 examples, and in part 3 I will consider 3 examples. So, total using 5 different examples I will demonstrate how to calculate the power consumption in comminution process using 3 laws of comminution. Example 1, in this example we have considered a problem where a material is crushed in a jaw crusher in which feed of average size of 60 mm is reduced to 10 mm while consuming 50 kilowatt per kg per second energy. So, we have feed of 60 mm and product of 10 mm, and while crushing we are using 15 kilowatt per kg per second energy. Now, what we have to compute? The energy consumption to crush the same material of 80 mm average size to 20 mm. Further, we have to calculate energy consumption for crushing same material, and the energy consumption will be computed using Kick's as well as Rittinger's law. Let us start the computation first using Kick's law. So, as you are very well aware with the expression of Kick's law, and it is basically E by m, that is energy consumption for crushing m unit of material. It is equal to Kk, that is Kick's constant ln df over dp. So, here we have if you see the first part of this question, here we have already given the energy consumption, that is value of E by m is already known to us, and it is equal to Kk ln df over dp. So, in first case df would be 60 mm and dp would be 10 mm. So, once we use these value in the expression, so E by m is replaced with 15 equal to Kk ln 60 over 10, and while after resolving it we can calculate the value of Kick's constant, which comes out as 8.3717 kilowatt per kg per second. So, here you see the unit of Kick's constant is equal to that of energy in the present case, because that diameter is in the ratio form. So, unit will be equal to as that of energy. Once I am having the value of Kick's constant, I can use this value of Kick's constant to calculate energy consumption while crushing material from 80 mm average size to 20 mm size. Now, why we are using same Kick's constant? Because now material for which I am calculating the energy consumption is same. However, its feed as well as product size will change, and therefore, we can utilize the Kk value which we have calculated over here as 8.3717, that we can use. So, finally, we have E by m which we have to compute equal to Kick's constant value, that is 8.3717 ln 80 by 20. So, using these value we can calculate energy consumption per unit of feed handled. So, the value comes as 11.606 kilowatt, and here if you see the expression and if you see the value, it varies from 60 mm to 10 mm and 80 mm to 20 mm. So, it comes under coarse crushing where Kick's law is applicable. However, in the present example the same problem we have to solve using the Rittinger's law. Now, as far as Rittinger's law is concerned, this is the expression of Rittinger's law where E by m equal to K r dash bracket 1 over dVsp minus dVsf. So, here you can understand that when we have discussed Rittinger's law in lecture 1 of week 3, there we have represented this in terms of a specific surface of product as well as feed, and in terms of this dVs, that is Sauter diameter, which is the volume surface mean diameter. And in this particular example, as we are given the feed, we are not given the distribution, therefore, we cannot use the Rittinger's law in terms of specific surface, we have to use the Rittinger's law in terms of sorter diameter or volume surface mean diameter. So, whatever value we are given for feed as well as product, that we can assume as the volume surface mean diameter. So, for feed, volume surface mean diameter is equal to 60 mm and volume surface mean diameter of product is 10 mm. So, that we have assumed to be used in this expression. So, once I use the value of dVSP and dVSF in this, E by m I already know. So, here I will write the value of E by m, which is given as 15, K r dash that we have to compute, 1 over 10, that is the value of volume surface mean dia of product, minus 1 over 60, 60 is the value of volume surface mean diameter of feed. So, considering all these value, that is energy consumption, mean diameter of feed as well as product, we can calculate the value of K r dash constant, we can say revised Rittinger's constant, and is equal to 180 kilowatt mm per kg per second. So, this K r dash value we can use to calculate the power consumption using Rittinger's law when we have to crush the material from 80 mm size to 20 mm size, which is the second part of the problem. Here we can calculate E by m value, which is equal to 180, the value of K r dash. We can use K r dash as it is over here, because we are using the same material to be further crushed from 80 to 20. So, here we will again assume that volume surface mean diameter of feed is 80 mm and volume surface mean diameter of product is 20 mm. So, considering the value of K r dash, dVSP and dVSF, we can calculate energy consumption per unit feed rate using Rittinger's law, which comes out as 6.75 kilowatt per kg per second. So, here you see we have solved a very simple example in which a feed size is given, product size is given, and we have computed the energy consumption using Kick's law as well as Rittinger's law. Here Rittinger's law we have used slight differently. Instead of surface area, we have used volume surface mean diameter of feed and product. So, this is a simple example how to calculate the energy consumption using Kick's as well as Rittinger's law. Now, here I have considered a complicated problem as example 2. Now, in this example what happens? We have a ball mill and this ball mill is fed with fresh feed, that is F, as 30 into 10 power 3 kg per hour or 30 tons per hour. So, feed to the ball mill, that we call fresh feed or we can call it make-up feed also, which is 30 tons per hour, and product P is screened using a screen of 295 micrometer aperture size. Now, where this F and P in ball mill, that we can see from this figure. Now, if you see this figure, this is the ball mill, and in this ball mill F1 feed is entering. Now, what is this F then? F is nothing but the make-up feed to ball mill. So, as far as make-up feed is concerned, we have denoted this with capital F, and the feed to ball mill is concerned, that we have denoted with F1. So, product of ball mill, that is capital P, is coming from ball mill after crushing, and this product is passed through a screen which is having aperture size of 295 micrometer. When this P is passed through this screen, some of the material is collected as undersize, and this we have denoted as P1. The oversize of this screen is undesirable, so that will be recycled back to the crusher. So, in this case F is the makeup feed and P1 is the final product. R we have denoted as recycle. So, the problem goes as oversize are recycled at a rate of 60 into 10⁻³ kg per hour. So, this R value is having the rate of 60 tons per hour. Now, what we have to calculate? The energy consumption of ball mill for open circuit as well as closed circuit grinding, and further we have to calculate the effectiveness of 295 micrometer screen considering oversize as the desired product. For this problem work index is given to us, that is 12.74 kilowatt hour per ton. Now, as we know that work index is related with the Bond's law, so we have to calculate energy consumption in this example using Bond's law. Example 1 have shown the computation using Kick's as well as Rittinger's law. Here I have considered Bond's law to demonstrate how the energy consumption will be calculated using this. Now, apart from this, we have the huge data for this problem which is shown in this table. Now, the first column of this table shows the mesh size, where the mesh size in terms of minus and plus are shown. Now, you understand very well that is what minus shows and what plus sign shows. Minus shows that material is passed through the screen, and plus shows that material is retained on a particular screen. So, in minus and plus format we have used different mesh size screen, and the size vary from 13.33 mm to 0.074 mm. So, the number of screens we have used are very significant. Now, what is the purpose to use this screen? Is to understand the particle size distribution of makeup stream, that is F, to the ball mill, the recycle stream which we have denoted with R, and here I am having the data of P1 which is the particle size distribution of final product which is passed through 295 micrometer screen. So, along with this flow rate we have to use this data to calculate energy consumption. Now, if you understand this problem, what we have to compute is the energy consumption for open cycle as well as closed cycle, and this is the diagram we are having which is basically denoted the closed circuit. If you understand the 5th lecture of week 2 where we have discussed different mode of operation for size reduction. So, the complete diagram shows the closed assembly of crushing. Now, in this diagram what is the open cycle and what is the closed cycle, or what is open circuit, what is closed circuit. If you understand open circuit, it says that material pass from one end to the crusher and will leave from other end of the crusher. So, considering this, if we understand the ball mill and we enclose the ball mill, where if I consider input and output stream to this enclosure, F1 would be the input and capital P would be the output. So, as far as open circuit definition is concerned, material which is passed into the crusher and material which is leaving from the crusher. So, F1 and P, if I am considering, it is the part of open circuit, and if I consider the recycle part inside this, then we can call this as a closed circuit, because closed circuit has some material which is undesirable which is continuously fed to the ball mill. So, if I consider closed circuit, then inlet to the closed circuit is capital F and exit to the closed circuit is P1. So, if I have to calculate power consumption for open circuit, I have to focus on F1 and P, where F1 would be the feed and P would be the product. If I consider closed circuit, then F is the feed and P1 is the product. So, I hope you are understanding what is open circuit and closed circuit in a crusher problem. So, here what we have to do, first of all we have to complete the data for computation purpose. Now, what is left in the data table which is given to us? In this data table, mass fraction of F, R and P1 are shown. For closed circuit, if I consider this closed circuit, F is used as feed and P1 is used as product. So, if you consider this table, here I am having the fraction of F as well as P1. So, here you can see the fraction of F as well as P1. So, for closed cycle, size distribution of feed as well as product both are given to us. However, if I consider the open circuit where feed is F1 and product is capital P, so you can see in this table no data of F1 as well as P is known to us, and therefore, we have to compute the size distribution of F1 and P to calculate the power consumption of open cycle. So, how I can calculate the size distribution of F1? By making material as well as component balance. If you consider this F1, that would be nothing but summation of capital F plus R. So, here we have F1 equal to F plus R, F is given as 30 tons and R is given as 60 ton per hour. So, this is the mass balance before entering to the ball mill, and component balance is F1 x1 equal to Fx plus R x R. And from here, as we have to calculate the mass fraction for F1 stream, so we can calculate x1 from this expression. X1 would be Fx plus R x R divided by F plus R, divided by basically F1, and that F1 we have replaced with F and R because values of F and R are given to us. So, if I consider the mass fraction for this particular interval, which is basically minus 13.33 mm plus 9.423 mm. So, for this size we can calculate x1 as 30 into F, that is 0.051 plus 60 into 0 divided by 90. So, using this expression for each size interval we can calculate value of x1. So, corresponding to first size, that is minus 13.33 mm plus 9.423 mm, the value of x1 has come as 0.017. In similar line we can calculate the fraction for other sizes also, and once I will calculate this, we can represent all F1 value in terms of x1. So, if you see, initially we have computed x1 as 0.017, that I have put over here, and further if I want to calculate this, so this into 30 plus this into 60 divided by 90. So, following the same expression we can calculate mass fraction of F1, which is the feed to open circuit. So, in this table all mass fractions of F1 for open circuit are shown. In the similar line, I can calculate data for P, because F1 we have calculated, now I have to calculate data for P. Now, if you make the balance over P, what it will give? P is equal to R plus P1. So, that is the balance, P is equal to R plus P1. If we make the component balance, P x P equal to capital R x R plus capital P1 x P1. So, we have to calculate x P, that is the distribution of this with respect to each size. So, x P would be equal to R x R plus P1 x P1 divided by R plus P1. Now, how we can calculate P1 value? Because R I know as 60 tons per hour, but how I can calculate P1? If you consider this closed circuit, what is the inlet to this is F and what is the outlet of this is P1. So, if we make the balance over this envelope, then F would be equal to P1. As in the problem, F is given as 30 tons per hour, So, the same value we can use for P1. So, F is equal to P1 for 30 ton per hour. Now, if I consider for this particular size, here both R and P1 are 0. So, no value we can obtain for P also. Further, if I consider second size, that is minus 9423 plus 6680, for this we can calculate 60 into 0.06 plus 30 into 0 divided by 90. So, XP over here we can get 0.04. So, following this method, we can calculate all fractions of P corresponding to different sizes. So, in this table all mass fraction of P for open circuit are shown. So, this is the complete data for open as well as closed circuit. In open circuit, what are the parameter? F1 we should know, and P we will know. So, for open circuit, F1 and P will be utilized to calculate power consumption. However, for closed circuit, F and P1 is utilized to calculate power consumption. So, this is the complete data for computation of power consumption using open as well as closed circuit. Let us start the computation for open circuit, where we have to consider F1 is feed and P as product. For closed cycle, F is feed and P1 is product. So, here we have to start calculation for open circuit considering F1 as well as P, and this expression we have to use to calculate power consumption. This is nothing but the Bond's law. Why we are using Bond's law? Because in the beginning we are given the work index of the material, so which automatically comes for Bond's law. So, in this expression you see what is dPb and dFb. dPb is corresponding to the size where 80% of product is passed through, and dFb is the size where 80% of feed is passed through a particular screen. So, if I consider the open cycle, there F1 and P are required to estimate dPb and dFb. So, what we have done over here, we have done the cumulative fraction of F1 as well as P. This is the individual fraction, and here I have the cumulative fraction, and you understand that if we do the cumulative from bottom, we have to represent the screen or mesh corresponding to negative signs. So, here we have cumulative of F1 and here we have cumulative of P. Now, this two value we will use for computation of power consumption. If you understand this graph, this is nothing but the cumulative plot of F1 as well as P. Now, dPb and dFb I have to compute according to the 80%. So, I will draw a line of 80% and then drop the line where I am having the cut at F1 as well as on P. So, dPb basically we can see from this graph is this value, which is 2500 micrometer, and dFb from this graph we can take as 5100 micrometer, which we have to show in terms of mm. So, 2.5 mm and 5.1 mm, because that is the requirement to be used in Bond's law. So, E by m is given here, which is 0.3162 work index, and all these value are known to us. When we put the value over here, we can calculate E by m. Now, if you consider this open circuit, here we have material in total as 90 ton per hour, because 30 ton from makeup and 60 ton from recycle. So, this value we have multiplied with 90. So, 68.76 kilowatt would be the energy consumption for open cycle. In the similar line, for closed cycle we will use F and P1, and here we will make the cumulative for F as well as P1 to know where 80% mass will lie. We make the plot over here for F as well as P1. This is the cumulative plot of P1, this is the cumulative plot of F correspond to 80%, we can draw the line and then we can calculate dPb and dFb as 3.5 mm and 7.15 mm. Considering this value along with work index, we can calculate the power consumption, we can calculate energy consumption per unit mass. If I consider closed cycle, the mass which is entering to this is 30 ton per hour. So, that m we can take as 31. So, this we can multiply with the 0.6467, total 19.4 kilowatt is the power consumption for this cycle which is closed. Further, we can consider open circuit and we can calculate power consumption using interpolation. Here for open circuit, F1 and P will be considered, and you see the 80% where it will lie from this table. We can calculate from interpolation also. How I can use the interpolation over here? Because between 2 point a straight line will lie, so I can definitely use interpolation. So, 80% will lie over here. So, dF would be lie in between these two. However, as far as product line is concerned, 80% will lie in between these two. So, dPb will lie in between these two. So, using interpolation we can calculate, and dPb I am finding as 2.437, which was 2.5 in the graphical representation, and dFb value 5.246 mm we can find from the interpolation. Using these two value along with work index, we can calculate power consumption. It will be multiplied with 90 ton. So, 73.95 kilowatt is the power consumption for open cycle. And similarly, I can calculate for closed cycle using interpolation. So, if I consider feed to closed cycle, F I have to consider, and 80% will lie in between these two. Similarly, in P1, 80% will lie in between these two. So, using interpolation I can calculate dPb and dFb, and further using work index as well as these values I can calculate power consumption. It would be multiplied by 30, and final power consumption for closed cycle is 19.92 kilowatt. So, this is the power consumption for closed cycle as well as open cycle. Now, finally, we have to calculate the effectiveness of 295 micrometer screen. If I have to calculate effectiveness to this, what is the feed to this is P, oversize is R, and P1 is the undersize. So, what is the desired product over here is the oversize. So, to calculate effectiveness of this screen, we have to consider these three columns which are R, P1 as well as P. And you understand how we calculate the effectiveness? We have to calculate YA, YB and YC. YA is the desired material in feed. So, in this case all these fraction combinedly will give the YA. YB is the R value up to here, and YC is basically the P1 value up to 295 screen. So, using this YA, YB and YC, when we put in this particular expression, we can get the effectiveness which is coming out as 78.09%. So, here I am completing example 2, and as far as this part of lecture is concerned, here I am stopping. I will consider example 3, 4 and 5 in next part of lecture 2. That is all for now. Thank you.